Hello everyone, welcome back to Energy Conversion System 1. Previously, we already talked about the impulse turbine, and now we are going to move on and talk about the other type of hydraulic turbine, that is the reaction turbine. Unlike the impulse turbines, where we mostly talk about the Pelton wheels as the main type of the impulse turbine, the reaction turbines, we will divide them into the radial type flow and the axial flow turbine. So to represent the radial flow turbines, we will be taking a sample from the Francis turbine. And as for the axial flow turbine, we are going to talk about the Kaplan turbine. So between these two turbines, of course, we are going to talk about the velocity triangle, the net head across the reaction turbine, and the turbine losses as flow. As for the axial flow turbine, we are going to talk about also the velocity triangle and losses. So unlike the impulse turbines, the reaction turbines in most cases work where the flow rate is high and the available head is low. So this is quite the opposite to the impulse turbines. So in most cases, we will use these conditions to differentiate between the impulse and the reaction turbines. Before talking into the detail about the radial flow turbine installations, there are several things that we need to keep in mind, that when we use a type of radial flow turbines, normally the available head will be between 30 to 500 meter. And another parameter is the specific speed will also lies between 0.3 up to 2.5 of radian. As an example of the radial flow turbines, in this particular slide we have the common sketch of the installations of a Francis turbine. Just as like the impulse turbine previously, the installation consists of the upper reservoir, and we have the pipeline, or the penstock as it's being called, where the fluid being flown up to the point before it enters the turbine. So point 0 is where the fluid enters the turbine, and then we will meet first the guide vanes, or a stationary blades, so to say. After passing the guide vanes, the fluids will enter the rotor blades, where in the rotor the fluids will flow radially through the rotor vanes and then exit to another reservoir under the turbines, or the area under the turbines, or the outlet of the turbines. We normally call it as the draft tube. And as the fluids interacts with some surface, pipeline, bendings and fittings, the first power losses that being experienced by the fluids is the frictional head drop, or small hfp, that is between this point up to point 0 here. We have hfp, or frictional head loss. After leaving point 0, as the fluid interacts with the guide vanes, we will have further power loss, or we call it small h g, This is due to the guide vanes, fluid interactions with the guide vanes. And further losses occurs when the fluids interact with the rotor blade, or we call it also as the runner. And the further losses is called as HR. So losses at the runner or HR occurs when the energy being transferred from the fluid to the turbines. And further losses, or the last losses, occurs as the fluid leaves the turbine and enters the draft tube. We have HD as the power losses due to the fluid interactions with the draft tube. In terms of the head available, so between the upper reservoir and the fluid level at the draft tube here, we have the available head of H1, and due to the losses of HFP, we will have the effective head, or H, capital H. And now let's proceed with the velocity triangle of a radial flow turbines. We already know from the constructions that we have these stationary guide vanes and the blade here that rotates. Let's say the blades move with omega to the directions, and we have the conditions at the inlet and at the outlet here. Let's say that we have the center point here, we have the R2 at the outlet, and we also have this is radius at the outlet, R2, and then we have the inlet radius of R1, and we have the last part as R0 as the conditions between the guide vanes and the blade. So as we know that as the water or the fluid leaves the guide vanes area here, it will flow with the absolute velocity of C1 as it enters the runner here, or runner or blade here, at an angle of alpha 1. And we also have the tangential velocity component at the inlet as U1. And we also have the relative velocity W1 at the inlet. And also we have the angle here between the blade. This is beta 1 at the inlet condition. And at conditions at the inlet of radius 2, here at this point, the fluid leaves at the blade angle of beta 2, and we also have the components of the absolute velocity C2, the relative velocity, and the blade speed at the outlet. And from these conditions, we know that the flow velocity, or the CR, at the inlet and at the outlet can be estimated through the volume flow rate divided by 2 times P radius at the inlet and the thickness of the blade. This is for the inlet, and also for the outlet we have 2P R2 thickness of the blade, or the runner at the outlet. Therefore, to get the Euler equations for radial flow turbines, we can write it down as E equal to W divided by mass flow rate multiplied with gravity. That is equal to U1 CX1 minus 2 U2 CX2. And if we have an ideal conditions, that means at the outlet Cx2 will be equal to 0. The Euler hat will only be the functions of u1 Cx1 divided by gravity.